Hey everyone, we'll now be moving on to more specific types of differentiation skills for specific types of mathematical ideas. But for now, do not throw away that knowledge because we'll be applying those knowledge about derivatives of algebra in the next few videos as well. So for the first part, right, we'll actually be talking about trigonometry. For the A level and O level syllabus, we'll be looking at y equals sine x, cosine x, and tangent x. And for the A-level kids, you'll get to learn a lot more trigonometry, the cosecant, cotangent, and the secant, and of course the inverse trigonometries as well. For the O-level people, you get to learn only 3 of these: sine, cosine, and tangent x. For the O-level syllabus, we are mainly talking about x is being in the radians and not in degree mode. For the A-level kids, well, you get to learn how to differentiate in the degree mode as well. Alright, but nonetheless, here we go. Well, I will just start off by talking about sine x and cosine x because they're actually quite related, alright? I will just write down the derivatives directly because there's not exactly a technique to it. Although for the A-level kids, you can actually try to prove these derivatives using the first principles and your Maclaurin series accompanied with your AMath 26. As you notice, sine x and cosine x, they're kind of like, a pair, right? If one is sine x, the other is cosine x. So as you notice, the derivative of sine x is cosine x, the derivative of cosine x is negative sine x. And obviously, if you compare the difference, only the derivative of cosine x has a negative sign. Why is that so? If you draw a cosine graph, so here I have a poorly sketched cosine graph. Here is 0, 1. Here it's pi minus 1. Here it's 2 pi 1. All right. If you notice, the graph has a negative gradient from 0 to pi and then positive gradient from pi to 2 pi. So you can kind of break this into two separate regions, 0 to pi and then pi to 2 pi, right? Let's draw a line across. Gradient from this region, as we noted, is less than or equal to 0. Well, just for information, at pi, this is a turning point, so gradient equals to 0. You'll get to learn more about this in the further videos when we explore the applications of differentiation. So in this region, gradient is bigger than or equal to 0 from pi to 2 pi. Now we look at sine x, right? We've already established that cosine x and sine x are kind of like related. So in this range of 0 to pi, we know that sine x is between 0 and 1. So in other words, positive, right? In this region, pi to 2 pi, we know that sine x is between negative 1 and 0. In other words, negative, alright? And you notice the gradient and sine x, they kind of clash, right? Gradient is negative, but in sine x is positive. Whereas in this case, gradient is positive, sine x is negative. To quote-unquote solve this, we add a negative sign to sine x, and then we are able to correspond to the gradient. So as you notice, here it's negative, here is negative. Okay, it fits. Similarly, minus sine x, 0, 1. Positive, positive, it matches. And therefore, minus sine x as well. You can try to use the same logic for sine x and cosine x. So if you look at the sine graph, so we have positive from 0 to pi over 2, negative from pi over 2 to 3 pi over 2. You can kind of introduce pi as well. You can be very more specific. Like from here to here, the gradient is actually increasingly negative. Whereas from pi to 3 pi over 2, the gradient gets less negative. And then from 3 pi to 2 pi, it's positive. And you realize it kind of fits the whole 4 quadrants of the cosine x, right? But I won't be touching into that. So now we have it. Sine x derivative is cosine x derivative is minus sine x. Now, we'll be looking at tangent x. The derivative, which I won't be wasting time to prove, is secant square x. Okay, which is kind of like the odd one out. But for the H2 math students, you'll get to realize that tangent and secant, they're kind of related. Sine and cosine, they're related. And cosecant and cotangent, they're also related, not just in terms of derivatives, but in terms of the property of sine square x plus cosine square x equals to 1 and blah, 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 blah. But mainly, these are the 3 derivatives that you need to know for trigonometry, for sine x, cosine x, tangent x. And this is kind of the basic, alright? Now we move on to more composite functions, which is the reason why I don't want you guys to throw away your knowledge for the algebra differentiation, because it's kind of like your power rule, right? So let's say I have sine 2x, right? When we differentiate this, yes, sure, cosine 2x, but we have to also differentiate inside the bracket, just like our power rule, correct? A power rule is basically, if you have fx to the power of n, the derivative, yes, the technique, right? Bring down the power to the front, reduce the power by 1. You have to also differentiate the inside and multiply it as well. Same thing for here. So the function is 2x, you differentiate it, give you back 2 cosine x. And let's give you one more example. Y equals to tangent x squared. The derivative will be 2x secant square x squared. The square does not affect the 2x because the derivative of x squared is just 2x, is not affected by the final power of the trigonometry. As such, we have this general formula. So y equals to sine fx cosine fx tangent fx, and the derivative would be f prime x cosine fx f prime x minus sine fx. Of course, you can put a minus sign at the front, no one's stopping you. And then finally, write it down here, secant square fx times your derivative f prime x. And this is your general formula for your trigonometry. Get this in place, and there we have it.